Excellent. Okay, so I'm John Plevyak. I'm also here with Pierre Sikora, and we're going to talk a little bit about putting WebAssembly extensions into network proxies. So the agenda is what the heck is a network proxy? Why do we want to put WebAssembly into it? And a little about the architecture of the ABI, the SDK, and again, I'll make this joke: if luck is on my side, we will have a demo. Okay. The network proxy is basically just a protocol engine. It sits in between, a client and some backends, and it handles protocols like HTTP 1, 2, 3, TLS, any L4 stuff like TCP or QUIC, and it does things for you. So it'll do things like authentication and authorization, routing, load balancing, caching, things like that. And one of the reasons why you'd want to use WebAssembly in this context is because you'd like to let, the proxy spend most of its time moving bits around and translating protocols. But when you get down to the business logic, it's helpful to be able to inject that in and not compile it directly in with all your underlying data plane stuff. So currently what people have a tendency to do is they'll build a module that maybe they'll either link in directly, or maybe they'll use a .so, or better yet, if they're lucky, they'll use like Lua, which is available in both Envoy and ATS. But unfortunately, Lua is kind of abandoned now. It's not been under active development. It's also not typed. It has some other issues, right? So a lot of people are interested in using WebAssembly. Why is that? Well, it's fast, it's safe. It's a web standard, and we love standards. And it's got a bunch of good implementations. You can use different languages with it. And primarily, it's useful because it's portably linkable and loadable. So you can, inject this business logic from the outside into your data plane using your control plane without actually having to reboot servers or anything like that. So that's really good. So what do we use it for in proxies? Well, of course, to avoid actually changing the proxy directly, but also we can use it for canarying, for doing A/B tests, for doing automatic rollbacks. We can inject complex behavior where we can have caching in there. We can go and make calls out to the control plane and then cache that and then use it for subsequent requests. We can use it for CPU intensive activities like transcoding, constructing pages out of templates, things like that. And, a huge win as, similar to Autodesk is that we can reuse existing libraries. If you want to bring in a library that you've, created for another purpose, or taken one that you previously were compiling directly in or loading in as a .so, you can now, compile it using the Inscripting toolchain, load it into WebAssembly, and then dynamically load it in, which is a huge win. Also, we have situations where, we've got customers. The customers have deployed, these proxies in their own networks, and now we want to inject code into those. Well, the customers already built the system. If we force them to redeploy a binary, that's a huge amount of work. But if it comes in as a control message, some configuration, a lot easier for everybody to consume. And the isolation makes for safer, more agile development. So if you've got, 10 or 12 different plugins and one of them starts crashing or causing problems, then it doesn't take down everybody else. So one of the things we really like to have is a standard for proxy extensions. So we want to have some common APIs and ABIs for these, and so that we can have portability between different proxies, because these proxies have unique characteristics, but they also have a lot of similarities. And when one evolves faster than the other, or your environment changes, or you do an acquisition or whatever, it's great to be able to move your logic from one to the other. And so currently what we have is a prototype in Envoy, and that's the URL. And we have a proof of concept in the Apache Traffic Server that implement the same ABI and API. And I will hopefully be able to demo that later on. So here's kind of the architecture of a network proxy. So the way proxies work is that they basically have a siloed each thread. So we don't like to have a lot of contention, and so we've implemented mapping of connections to individual threads, And then there's one or more WebAssembly VMs in each thread, so they're replicated. So, for any VM you decide to configure, it's going to be instantiated once per thread for each of the worker threads that's going to do the work. And then there's also a collection of singleton services. So you might have a background process, for instance, that scrapes a bunch of statistics. It's going to send it out to some backing server. You only want to have one of those, right, per box. And so there'll be a singleton that'll do that, and it'll talk to the other individual thread VMs and collect all that information. And then in order to communicate between these things, we have both shared data and also message queues. So you can, send a message to say a service, telling it what you want it to do, and that's how we manage the inter-thread communication. Okay. So I think this is basically just in words what I said before about the architecture, that each VM is single-threaded, etc. Okay, so what kind of extensions can you write into the proxy, and what kind would you like to write? So from a server standpoint, that's the singletons. You might want to manage like lifecycle of the process, and you might want to handle logging and statistics, aggregation, summarization, stuff like that. From the standpoint of individual operations coming to the proxy, you're going to deal with things like remapping, which is routing and redirection, HTTP, transcoding header changes, authentication, stuff like that, etc. And then you have the sort of generic stats and logging APIs. So the way we decided to do this implementation is we broke it up into API sort of layers. And the first layer is just the straight VM API. So when we first started, the C API for WebAssembly wasn't really super well established, right? And so what we did is we created our own little layer, which is even smaller. And it makes it really simple to implement a nice little sandbox that does just, sort of the bare minimum. And so we've got support right now for WAVM and V8. We haven't done WASM time yet because we just haven't had time. And we have what we call the Null Sandbox. So basically you can take the existing WebAssembly APIs and then compile the code directly into the proxy. And why would you want to do this? Well, primarily you want to do it for, say, debugging purposes, because you can put a debugger on it, right? But it's exactly the same code that you'd run otherwise. So it's, the Null Sandbox isn't really meant for production, although, frankly, we're using it that way right now as we continue to develop our code. And there's only a few operations that that we need from a runtime, and that is a way to register callbacks. These are calls coming out of the VMs. These are API calls, and you need to be able to get a function. So calls that you want to make in all your hooks that you're going to do. You need to load, link, and start the code, and then, instead of trying to share memory, because that's still sort of a work in progress, we're just copying code or memory in and out of the VM. And so there's really only two other functions, set memory and get memory. Yeah, so this is kind of just a little more detail on that. The memory management is copying things in. It's simple, but not very efficient. Hopefully we'll get good shared buffers at some point that we can use those for things like transcoding. There are some trade-offs in picking the different VMs. WASM time supports ahead of time compilation, as does WAVM. V8 doesn't currently support that, but V8 has a lot of miles on it. As a Googler, I can have support from the V8 team, so that's a big plus from my standpoint. But it depends upon your situation, and that's why we have a common API and we allow you to sub out the runtime. And a great thing is that when something goes wrong and you get a seg v because you're running C++ instead of Rust, and you got a null pointer, you can choose what to do. So you can set your policy. Is this just a reporting plugin, in which case you might just fail open, you don't care that much, you report it, or if it's something to do with authentication, for example, you might fail closed. So on the ABI front, so this is the low-level interface, we want to make sure that we can support different languages. We want to allow for, implementation-specific stuff. And so we prefix everything with a name, a fixed name when it's portable, and a different name when it's not portable. And currently, we're having all the functions return a common error interface, so like error no. Because this is low level, you're not really expecting the users to deal with this, but we do want the API implementers to have access to good error reporting. And data is always passed out by pointer because the external process can read directly from the buffers. But when data is passed in, we allocate inside the VM, and then we pass ownership into the VM. And so it's always the responsibility of the code in the VM to free the data. And for the existing SDKs, that's relatively simple because for C++, we can use smart pointers, and Rust can take care of itself. They're good at this. So, okay. So the kind of APIs that we support are like, periodic events, getting and setting metadata, HTTP and gRPC fetch, remotely. These are kind of higher level interfaces, but they're generally useful. Logging that plugs directly into whatever logging system is conventional in the language. So, in C++, that's going to be standard error, standard out, and in Rust, it's going to be the built-in log functions. And then, statistics, share data, and message queues. So this is what an ABI looks like. So in this case, we're looking at the GetTime function. So we've got an extern function called Proxy, get current time in nanoseconds. Since it only returns, a WASM result, we have to pass a pointer out to where it's supposed to write the time. That's going to get verified on the outside to make sure that chunk of memory is valid before the thing gets copied in. And then on the implementation side, we have a handler that has takes words, right? So we want to be able to support the NullVM, which is going to be probably 64-bit, right? Because it's a host architecture size. We want to support WASM 32 currently. We want to make sure that we're ready to support WASM 64. And so we have this abstraction of word, which is, and on the host side is always 64 bits, but on the inside the VM is often 32 bits. And then the implementation of the handler is going to, it carries with it a context which describes the request on the outside that's being processed, or whatever other contextual information we need in order to handle the call. And then we use that context to get whatever that information is in this case, because the time nanoseconds is sort of generic to the machine. We don't really need to use the context for it. But say it was like get request header, it would need to use that context information to figure out what specific request header you wanted, right, for that particular request. And then you have to validate the memory address that was passed to you, and then set the data into the VM. And if there's a problem setting the data, you have to return an invalid memory access to the VM. And the implementation of get current time in nanoseconds is not context dependent, but it's just grabbing the time from the system. Okay. So to give you an idea of like what we decided to do in terms of like the ABI versus the high-level API, we're going to look at like defining metrics. So the low-level one, it just takes a string, which is like the name pointer and name size, a metric type, and it returns a 32-bit number, which is just a token to represent the metric. And then when you want to increment it, you pass in the token, you pass in the amount you want to increment, and increments it. On the high level, we want to support all the normal high-level things you'd expect. So in this case, you have a collection of different tags that have types. You've got functions that allow you to increment something by passing in values of the appropriate types, and the templates do all the magic to concatenate all this stuff together and turn it into a single string. And then you can do you have an interface to like resolve it, so that converts that set of tags into an ID, so that when you do this increment, it's going to be fast, so just one function call. So this is kind of the dichotomy we have, where it's like really low level versus language specific high level API that's like, feels comfortable for your, C++ or Rust program or whatever. Okay, so if you're trying to build like a plugin for HTTP control, this is the kind of thing you'd see, right? You've got this context that represents a particular request. You have one of these is instantiated per request, and it has things like, in this case, on request headers, which means, okay, request came in, all the headers are available, here you go, do what you will. And then inside that handler, you can do, you can log, information, like in this case, a debug log. You can ask for a request header and get it. In this case, well, the code's a little off because he's asking for host, but he's calling it path. But you get the idea. And then you can change the headers, and then you can tell the state machine, which exists, in the surrounding environment, what you want it to do. In this case, once you change the headers, you're saying, okay, state machine, you're ready to go. Continue on, get the body, forward the request, do what you normally do, because I've made all the changes that I want. And then on the bottom here, we have a registration thing, so we can register this class with the surrounding system and tell it that this is the thing you want to instantiate every time a new request comes in. And so it's relatively straightforward. If you're a proxy programmer, you'd be like, okay, I understand how this is going to work. I could probably make this happen. Okay. Yeah, so this is a much more complicated example, which I'm actually just going to skip over, because if you're not a proxy guy, you probably don't care. Okay, so the current SDK development environment we have is a Docker image. And the reason why we went with Docker is because Inscription's a little tricky, and because in order to use Inscription with protobufs, you need to have a patched version of that library, and it needs to have been precompiled. Well, or you can compile it yourself, but it's a little bit trickier than one might like currently, because the Inscription target is not naturally available for all your libraries. So it's often helpful to have these things sort of precompiled, and a Docker image is a really great way to go. So what we do is we provide Inscription, the Absol libraries, protobufs, and also WAVM. And the reason we supply WAVM is because WAVM has this ahead of time compilation mode. And so as part of your tool chain, you might want to like precompile the code, WebAssembly code, so that it'll load very quickly. And in Proxies, this is pretty useful, because if you dynamically update it, you don't really want the whole thing to just hang up for half a second while it's compiling the whole thing. Now V8 is different, because V8's got a staged compiler. It can get started really quickly. But WAVM, for example, uses LLVM JIT, and it basically just hangs your system for a short amount of time while it's compiling the whole thing. So doing the pre-compilation in a controlled environment is really the safest way to go. So we do support installing all these things manually. We have a nice documentation on how to do it, but I wouldn't suggest it. A little bit more work. Okay, so I do have a demo. Let's see if I can get this to work. Okay, yeah. Let's see if this thing is going to do it for me. And who knows? Okay. All right. So first I'll just show you the demo, and then I'll just show you what some of the. Okay, maybe not. Okay. All right. Yeah. So oh no, it came back. Who knows? Don't touch it, right? Okay, so this on top here is Traffic Server, and it's pointing to a particular WASM file. And I can actually show you which one it is. User local, etc. Traffic Server plugins. So it's pointing to one that's in the Traffic Server plugins experimental WASM example HTTP. Okay, and if I run it. Maybe. Oh, there it goes. And I run. It will it will print out, as you can see on the top, all the headers. And on the bottom, you'll see that it has added a header called XWASM response ATS WASM 10. Okay, so that's what it's done. And but we can actually run the same exact plugin over on Envoy, and that's actually the kind of the fun part. So if I go over to Envoy and I look at, let's look at the envoy.yaml file. Yeah, so the Envoy YAML file is pointing to the etc. Envoy filter. But if I go and I look at that one, it's actually pointing over to the experimental WASM HTTP one. And then if I run it, it's going to do exactly the same thing. It prints the headers out and it inserts the ATS WASM 10. Which is kind of cool because now I have two completely different code bases that are running exactly the same code with the same API, and that's quite useful. So now if I go to, I'll just show you what it looks like a little bit. Let's see, plug in experimental ones. So like the Docker file is just, it just builds the Docker file using this SDK container, which, does normal Dockering stuff to install the various tools and protobufs and stuff like that it needs, and Absol on very specific versions that we support. And then if you look at the example HTTP code, you can see that it is basically exactly the example that I showed before, except there's a couple different handlers that just log stuff for you. And then that code, and then we can change it very easily. So let's say we wanted to change, it's like instead of saying -10, you'd say -20, right? And we can, well, accept that, yeah. And then you can compile it, just running the Docker compiler. Docker version, hopefully, yeah. So here it is. It's inside Docker where we fire it up in scripting, and it's gonna compile it with all the different flags that we need. And now if we run it again, we can see that it's now saying ATS WASM 20, and we can go back and do it with Envoy as well. So I guess the take home from this is that we're trying to standardize this. We're trying to get this to be part, hopefully, of like the set of modules associated with WASI, because a lot of people want to do HTTP type stuff. A proxy is only one example. A lot of people also want to do it as sort of a file server, plugin, right? Something like Lambda-like. But this is just some additional functionality on top of that. But it's functionality that is important to one community and also would enable other use cases. And I think that there's a lot of opportunity for different groups who've got different use cases to try to standardize a common set of APIs so that you can get portability from environment to environment. Like we have portability in between browsers. Now we could have portability between proxies and other environments. So if anybody's got any questions, I'd love to answer them or show you some more bad demos with too small words.
Thank you. That was really interesting to see all these different uses of WebAssembly. So that's great. Can you elaborate more about the Null Sandbox? Is it still using WebAssembly but compiling?
No, so it's not using WebAssembly, but the key is though that you can use exactly the same APIs. So the thing is, the WebAssembly compiles down to a 32-bit system, right? And so all your pointers are 32 bits, so it's a little tricky because now every time you want to pass something in or out, you have to think to yourself, well, is that going to be a native system word? Is it an address? Like, what data type should I use? But what we did is we abstracted that all with those words, and we have functions that know how to copy in and translate addresses into offsets into WebAssembly, or just leave them as native addresses. And it's a little tricky also because in WebAssembly you could just create a global variable, right? And that variable then is, there's only one of them, right? But there's one of them per thread or one of them per VM. And that's not something that's possible if you're using like a Null Sandbox, because you'd be compiling this thing directly into whatever underlying system you have. So instead, we created this concept of a root context. So when you add a plugin to the system, it creates a context which is global to that plugin instance. And then the idea is that anybody who wants to use a global variable would then put it inside the root context. And that works portably between the Null Sandbox and everything else. And another point that I should probably make is that we have a hierarchy of sharing. So you can have a large number of plugins pointing to an individual VM, because there's a lot of overhead associated with the VM. And the larger the VM is, the better able it is to handle situations where there's a sudden rise in the use of memory and then a decrease in the use of memory. If you have a lot of them and you do that, then you end up like fragmenting your memory and wasting a lot of it. So it's very useful to if you can, compile a lot of plugins into one VM. And so we have this idea of like a bunch of plugins that then map to a smaller set of root IDs or root contexts, and then a bunch of root contexts that then map to a single VM. And so when you do that register thing there, you can actually register a whole bunch of different handlers, each with different root contexts that then are basically used for routing calls from particular plugins into the same VM, but separating the logical code. And I actually think that that's a useful, innovation for a situation where you're trying to do a plugins like this, because Istio, for example, wants to deploy a pile of plugins, right? But if each one of them, Envoy uses two workers per thread, and if you're running 32 threads, that's 64 plus some overhead number of workers. And if you're running 10 VMs, right, and each one's taking 10 megabytes, and you're running 64 of those, that is a heck of a lot of memory, right? So you really, want to control that. And so having some way of multiplexing these things down is actually quite useful.
Thank you.
If I'm running Envoy and I want to add a plugin and I'm worried about that plugin misbehaving, what kind of protections do I have against like a misbehaving plugin? A simple example is like a plugin that just never halts.
Okay, so right now, for WebAssembly, we have a proposal which we have not implemented, where we're going to, instrument the binary. We're going to do a WASM to WASM translation, where we insert, pseudo instruction counters, and then we can throw an exception if they exceed their limit. So until that gets implemented, we're gonna just throw a timer on it, and then just throw an exception out of the timer. But the plan is to put instruction level limits within it by doing WASM to WASM rewriting. It's like there's a project, I can't remember, it's like Kimona or something that does something similar to that. Maybe it's not named that. I can't remember. But there is a project that does WASM to WASM rewriting. It does it mostly for instrumentation purposes, so it lets you add hooks in. But we can use a similar process to deal with this.
So then the idea is that you could have untrusted plugins operating in the same proxy, like essentially hostile plugins, like sitting next to each other in the same process.
You could. So, it depends upon how paranoid you are, obviously, right? So, we have talked to like the VA team, and I would have to say, so depending upon who you talk to, like, you know, and your level of comfort, the question is how hostile are we talking about here, right? So there's like third-party plugins that a customer might put in, right, where you're accepting a certain amount of hostility, or maybe like, you know, junior developers, right? And then I took some random person who didn't even give me a credit card's code off the internet, and I injected it directly in. Well, at that point, you might consider wrapping it in another process boundary, right? Because, you know, as safe as V8 is, there are people who occasionally escape that sandbox and end up in the next sandbox. So, yeah.
That's a follow-up. And that's the so you said you're using WAVM with ahead of time compilation. So that means you can like you're basically just loading the shared object version of that WASM file.
Yeah. So if we're doing that, the thing is that you want to do that in your control plane. So you have control of that compiler, right? You wouldn't accept one from the outside.
You're trusting their compiler in the same way that you trust the V8 compiler.
Right. But you'd want to have control of that compiler. So, you know, when somebody injects it into the control plane is going to do the compilation rather than trusting the code that comes in from abroad. Yeah.
I think that's really great what you are doing. So what's the current status of this initiative? Like when can I use it in production, or this is like just experimental project?
Oh, no. So at least the Envoy version, we're currently in the midst of upstreaming. So far, we've upstreamed the VM interface, and we're currently upstreaming the V8 version of the interface. Then after that, we're going to upstream the ABI, and then after that, we're going to upstream the SDK. We have it already in a branch, and we're actually using that branch, and Istio has an experimental version in that branch. But we're also talking with some of the standardization people to try to get it standardized. So like the specifics are still in flux. So if you did adopt it, it's likely to change, you know, rapidly.
So I'm trying to understand how can I use this. So does it mean that I can send some signal to Envoy and tell, hey, reload this plugin from the disk, or load new plugin?
Yeah, so Envoy in particular has this configuration system called XDS, which is basically like a system where you can just send it a whole new configuration. And the configuration itself describes like the set of filters, they call them filters, which are essentially the plugins that run when requests come in, right? And those filters can be a WebAssembly filter, and then it has a payload, which can either be a file on the disk, for example, if you've already pre-pushed it, or it can also be, well, soon, you know, that we've got the PRs outstanding, soon it will be also a URI, right? So you could have another server someplace, and hopefully with certificates, et cetera, and then you could just grab the code from over there.
Yeah, because it was my next question. How would it work in Docker environment, for example? If you're running container, usually do not change files. So basically,
right.
You send the signal and tell, hey, update this from URI and.
Right. So that's the idea.
Yeah. And the last question: How does performance compare to, say, Lua in Nginx? You benchmark.
Yeah. So we did some like micro benchmarks, and I know like the performance, like the raw performance is like 1.5. So it's like, you know, you lose like 50% or, you know, 33% like on CPU. But there's a bunch of cost on the crossing in and out of the VM. So we have a baseline, which is calling in and then having the inside call out to get, you know, time, right? Which is just a register access, and then calling back in again. So the base cost is 100 nanoseconds, and it costs in WAVM about 200 nanoseconds, and in V8 like 230 or 240 nanoseconds in order to do these transitions. So you're paying maybe 100 to 150 nanoseconds in order to do a call in and a call out. So you could figure it's maybe, you know, 50, 70 nanoseconds for a transit to go, you know, across the VM boundary.
So another question: how complex things I could implement is in this system? For example, if I want to support dynamic domains, like do SNI, so basically request comes, I go to database, download certificate, and like provide it like during TLS handshake? Can you do something like this with this?
So we don't have an interception at before TLS right now, but that's a good point. We that's an interesting API point.
Yeah, because right now we are looking.
You could talk to actually Piotr might be able to answer this better than me.
So right now we expose both HTTP APIs at layer 7 as well as low-level by stream. And if you really want, you could in theory implement TLS in WebAssembly and just use it and read encrypted packets from the wire. Yes.
Yeah. I don't think we have any happy APIs for that though. Like we don't have just like specific callouts for that, right? Yeah.
And do you have specific API to open TCP connection from a plugin to external host?
So currently we don't. We just have HTTP and gRPC, and the reason is because all the policies set on access are set based on like these clusters of things you're allowed to talk to. And so it's more of a security thing than it is actually like, it would be easy to do. It's just like, also you want to be safe, right? So yeah, I guess that's the answer.
If I wanted to say accept third-party or untrusted plugins and give them not arbitrary APIs, but like lock down the specific APIs. To say I don't want them to be able to make HTTP calls. I don't want them to be able to access system time even. Like I want just to completely, you're allowed to do stateless, entirely WASM things. You're not allowed to make any callbacks out to the external environment. How would I do that? What's the story around sort of like limiting the capabilities of plugins?
Yeah, so we don't really support that yet. So I think we're going to kind of lean on the WASI guys have this idea of like, capabilities and being able to like control, accesses, down to the individual, files and sites you can contact and the APIs you can use. And, I'd rather just like, lean on them, right? Because they're already working on it.
WAVM has a, that's a tongue twister, a WASI interface implementation already.
Yeah. He just added a little while ago.
Questions? Any more questions? Cool. Let's give a round of applause for John and Peter.
Thank you.